The topic I'd like to talk about today is kind of how we can better understand neural networks that are deep but very wide. Before I start, I'd like to thank or acknowledge all of my collaborators, Jae-Hoon Lee, Roman Novak, Jeffrey Pennington, Sam Schoenholtz, Joshua Zoldikshi, and Liqiao Xiao, and as well as Jerry Huron and Greg Yang for collaborations on some of the work that's going to be talked about in this talk. And so what's the motivation for this talk, for understanding neural networks that are very wide? Well, at the moment, we're still trying to understand how neural networks work. They seem like these very complicated black boxes, which we hyperparameter tune and don't really know what's going on internally, what's being learned, how to train them better, why they generalize. So where can we start? Well, oftentimes in the theoretical sciences, particularly in theoretical physics, a very promising approach has always been to try to, when you don't understand something, to try to take the limit in some sort of variable and see if you can solve it exactly or what happens in the limiting case. And then after you do that, to try to back off of that limit and kind of do perturbation theory about that limit. And that's sort of the overall kind of picture I want to paint for where this line of research could go in trying to understand how neural networks work and how we can better describe their learning and generalization dynamics. Now, oftentimes when you do something like that, like take a limit, try to come up with an exactly solvable model, you hope that the limit that you took was of practical interest or of interest to experiment. So the sweet spot is, can you find theoretically tractable settings which are also of practical interest? And it turns out that this one is one that kind of has a little bit of both components. So there's been many papers, and I'll show you some plots from our work and as well as work by other people. There's been a general kind of empirical observation in the field that wider networks generalize as well as their narrower counterparts, or even better. And this is part of the mystery behind overparameterization. Why do overparameterized networks, at least past a certain kind of critical threshold, you just keep making them more and more overparameterized and you do better and better? And you can see this here in this sort of kind of vanilla setting for fully connected networks, where you look at the generalization gap, and the best performing the networks with the smallest generalization gap are the widest, and you see this very nice trend as a function of the network width in this fully connected setting. Here are some other plots kind of displaying the same trend. On the right, you have convolutional neural networks with pooling. Here, the width of the network refers to the number of channels in a convolutional layer. In the fully connected setting, it refers to the number of hidden nodes. And as you make the layers wider and wider, in this case, you see that the accuracy of the test accuracy of the resultant networks is increasing. Likewise, on the left, this is kind of an aggregate plot over depth and width, but the overparameterized ones are generalizing the best. And those were plots from some of our papers, but certainly some earlier work had also demonstrated this. In particular, I was very much influenced by these plots in work by Nishapur and collaborators that also kind of did these similar experiments, just increasing the width of networks and seeing that the test error tends to go down. So it's natural to ask what happens in the limit of infinite width, and this seems to be, also of practical interest. There's maybe a different kind of motivation also behind what I'm going to talk about, which is that maybe some things kind of simplify when you take a perspective of thinking in terms of functions that are computed by neural networks, the perspective from function space. So when I first started working in this area, I felt that a lot of the research literature took a very parametric point of view. So a lot of people were talking about the loss landscape, the non-convexity of the loss landscape, critical points, and that sort of thing. And that's very important to figure out, but sometimes it's good to remind oneself that the thing that you're interested in at the end of the day is the function that is learned. And particularly when you tie in with like problems in science where people have maybe intuition for what kinds of functions they would like to learn or be biased towards, that sort of thing is nice to kind of be able to characterize in the neural network setting. So one question you could ask is like, what sorts of functions are we biased towards at initialization? What sorts of functions are we learning after we train with a certain algorithm or we have a certain architecture? And so the kind of direction we're going to take now is like if I give you a distribution over parameters, that could be kind of a random distribution. Maybe in a trained network, it's a very correlated distribution, and I give you an architecture. What is the distribution over functions that corresponds to that combination? And that sort of concept was something that was very nicely highlighted in a paper by Radford Neal now dating back to the mid-90s, where he kind of advocated for that sort of perspective for describing a single hidden layer neural network. What I'm going to talk about now is sort of the extension of that to the deep case. So he identified it for the single hidden layer network. Deep neural networks weren't popular, then they became popular again. And now we're kind of revisiting that line of work, that correspondence, to see what we can kind of extract from it. So the correspondence is the following. Let's consider a fully connected deep network with fixed depth, but it can be arbitrary, so depth L. You send in some input into the network X in R to the D. You have some parameters, the weights and biases of the network. And let's say the crucial point is that the prior over parameters, at least for this setting that I'm going to talk about, that they be IID, and also that the variance of the weights, here I'm going to just draw the weights from a normal distribution, that the variance of the weights scale as 1 over n, where n is the network width. And so what that means is as you make the network wider and wider, each weight or each edge kind of in this network contributes a vanishing amount. But that's important. They nonetheless, when you sum up all the weights together to get the contribution to a particular hidden node, there's still an order 1 contribution to the function. They're just it's being distributed more over more parameters in the weight matrix. So given this IID prior over parameters with this particular form of scaling, which is the one we tend to use in practice, precisely because we want to keep hidden nodes to be of order 1, this gives rise to a particular class of functions when you take the infinite width limit. And so to introduce some notation here, let's say that the computation that a neural network does is this following iterative computation, where these z's refer to pre-activation values. They're the they're the function values that go into a hidden node before a nonlinearity is applied. L denotes the layer, I denotes the hidden node index, and ZL is, of course, it's gotten from, typically for a fully connected network, it's gotten by an affine transformation applied to pointwise nonlinearities that are applied to the pre-activations from the previous layer. So given that computation, imagine now that you kind of follow what happens to the input X as you pass it through a network that is initialized in this way. Because every time you have an affine transformation, and these are IID, and you have infinitely many random variables now, because you've taken n to be infinity, you can essentially apply this central limit theorem one by one. So imagine you're going through the network, you take each successive layer from the input to the output to be infinite, you apply the central limit theorem, and so from that, for any finite collection of input points that you follow, you're going to be governed, the pre-activation value ZL sub I is going to be governed by some multivariate normal distribution, or the generalization of that here is the Gaussian process, or Gaussian field theory if you like, if you're in physics. And so given that application of the central limit theorem, because the width is infinite, the question now becomes, how do we characterize the Gaussian process? For us, because all of our parameters will have mean 0, the Gaussian process will always have mean 0, but all of the information, interesting computation, is being condensed into the computation of this covariance function, the second moment. And I've written the expression here for that, so k to the L is the covariance function corresponding to after L layers. It's a function of 2 inputs x and x prime, and it's gotten just by plugging in this iterative computation over here for the z's. It's gotten by computing this expectation value the product of two nonlinearities, given that the pre-activation z to the L minus 1 are coming from a Gaussian process from the previous layer, described by a covariance function k to the L minus 1. And this is just notation. It's basically just two points that you're sending in. They're governed by a Gaussian distribution, so it's a two-dimensional Gaussian integral. And to compactify that form, this is this like boxed equation. And so there's that 2D Gaussian integral you can do. Sometimes you can do it analytically for certain nonlinearities. Sometimes you can't, and we approximate that numerically. But to just succinctly summarize what that recursion relationship is, k to the L is related to k to the L minus 1 via some function c sub phi, which is the function that comes from computing this integral, and it only depends on the choice of nonlinearity phi. Otherwise, the functional form is governed by the actual k to the L minus 1. So this is this correspondence that like a deep fixed depth infinite width network is governed by this Gaussian process with this particular class of compositional kernels was something we derived and published in ICLR of last year. It was also simultaneously derived in nice work by Alex Matthews and collaborators. And of course, it dates back to this single hidden layer case by Radford Neal. So this is sort of the map that you have in terms of the computation that's being done. So on the left, you have the iterative computation where you apply affine transformations and pointwise nonlinearities, and you get the pre-activation function. So you send input signal x in, you get these z's all the way to the end of the network. And then as you take the infinite width limit, you also are getting essentially an induced mapping on the k's, these covariance functions. And you relate one layer to another via these c's. So from k sub 0, which is your base case, it's just an inner product of the inputs, x and x prime. You take this very nonlinear map C, map K0 onto K1, and so on through the network. So the computation that you do on the left for features or representations gives rise to a computation you do among second moments. In the infinite width limit, that's the only kind of computation you do, but you could imagine that as you back off of the infinite width limit, if I were to continue drawing columns into the right, there would be maybe some recursion relationships that govern the other higher moments, and so on. So that's sort of the map for the computations that are being done. And so far, right now, we just have a description of the prior over functions. We're only talking about initialized networks, but we'll get to trained networks in a minute. So what I alluded to earlier is that for some of these cases, the recursion can be computed analytically. This is something that was known also in a paper by Cho and Saul, as well as others. And here's the explicit expression for a ReLU network. This is ReLU fully connected network. And so you can just write it down. If you were to try to visualize the kernel, it would actually look pretty simple, which is surprising. So this plot here is showing the angular dependence of a ReLU kernel when you have two inputs, x and x prime, and you just rotate x prime by angle theta from x. And what you see is like a very shallow network would basically follow a cosine theta. That's because that's x dot x prime. And as you push that covariance function through a deeper network, what's happening here is that it's becoming flattened. It's losing a little bit of its structure, but it's nice and smooth in this case. And on the right, you also see some samples from a Gaussian process neural network for just a 1D function. And this is a 1D function, depth 10, fully connected neural network, and the corresponding Gaussian process draws of it in the 1D function space. So before I talk about trained networks, though, I want to take a quick aside and talk about a whole body of work, or reference a whole body of work that is very much tied to this, because it's studying the properties of essentially these covariance functions in a particular regime. So what's the idea here? Well, can we extract kind of some prescriptive value from this correspondence? And this line of work that is maybe more broadly referred to as mean field theory or signal propagation or deep info propagation takes this point of view. So basically one heuristic you might imagine for how to come up with a good initialization scheme for a deep neural network is that you should at least be allowed to propagate the second moments of the data through the network. And that's essentially this, that's as if you had worked in the infinite width limit and that's the only information you had. So imagine that you took this recursion relationship from K0 to K1 and so on via these maps C sub phi and studied what happens as you iterate this with depth. So for fully connected architecture, what ends up happening is you approach sort of boring fixed points with depth. That's because you lose contact with the signal. This depends, how fast you do this depends on your choice of hyperparameters, but essentially the signal just goes in at the very beginning, and imagine you iterate this for hundreds or thousands of layers. You approach boring fixed points, but depending on how you choose these hyperparameters, so in this case explicitly that would be the bias variance, sigma b, the weight variance, so these were the hyperparameters that govern the prior over the parameters. And also the choice of nonlinearity those choices dictate how rapidly you approach the fixed point as you iterate. And so you could imagine, there's a certain scale over which you start to lose the structure you originally had in the data. That scale, that scale in terms of number of iterations is an effective depth scale for how deep of a network you're essentially sending in that information about the second moments. And so you can kind of see here, so these are sweeps of the depth of a network as you sweep one hyperparameter, the weight variance in this case, and the red regions are showing places in this 2D phase space where you get good training or get high training accuracy. And you can see basically for very deep networks that as you sweep weight variance along this x-axis, there's only like a sweet spot, a narrow range where you are actually able to train. And in a lot of these other regions, the regions that are dark, you're not able to train. And that's because in those regions, whatever effective length scale you've induced by choice of hyperparameters, by how rapidly these recursion relationships approach their fixed points, that depth scale is too small compared to the depth of network that you've chosen. And so you need to, it's kind of a prescription for how you should choose your hyperparameters and also given a certain depth network that you'd like to train. And this is, again, more of an aside, but it's essentially studying the same covariance function, again, talking about the priors over functions. And there's a whole body of work, starting with a paper by Ben Poole et al. And Sam Schoenholz et al. And continuing that basically looks at these fixed points and makes phase diagrams as a prescription for initialization. So that was an aside. Let me go back to talking about trained networks in the infinite width limit with some kind of training. Now that we kind of made this connection with Gaussian processes in the infinite width limit just at the level of the prior, we can basically just do textbook Bayesian inference if we'd like to do that. So Bayesian inference with the GP is very easy if you're thinking about mean squared loss. And the reason is that if you imagined kind of writing out how to do Bayesian inference in function space, all of these, the entire integrand would just be a Gaussian integral that you would do over finitely many points. And so you can do it exactly. And the result is that if you wanted to, the predictive distribution or the prediction Z star for the function given for the model given some test point X star and some data set D is governed by a normal distribution with a mean and variance mu bar and k bar that are written explicitly here, and it just amounts to doing some linear algebra using the covariance function evaluated on the training data and also the test point. So explicitly you would construct this case of DD is the covariance function evaluated just on the matrix corresponding to the training data set. So it's an n by n matrix if you have m data points. You need to compute the inverse. You need to take these inner products with the target, with the labels y, and also with this other vector here that's constructed using the test point. But it amounts to just doing linear algebra. But it's linear algebra involving large dimensional matrices, so that's one thing, but nonetheless, you can do it exactly. So at the time that we did this is now dating back almost like a year and a half ago, we implemented this Gaussian process exactly. We did Bayesian inference, either using like these exact formulas we had for ReLU or numerically for other nonlinearities, which we couldn't. So we implemented that. It's just restricting to the case of mean squared error and kind of doing regression on one-hot targets. So that is still quite a bit different from training with cross entropy. But because we wanted to have an apples-to-apples kind of correspondence or comparison between neural networks and Gaussian processes, when we also looked at finite width neural networks, we trained with MSE loss and just wanted to see how well they would do when we trained with SGD as opposed to this linear algebra computation. And what you can see here basically is that what we found was that oftentimes for these data sets, at least for MNIST and CFAR, the Gaussian process did as well, if not better, than the finite width neural network. And this is a neural network that is hyperparameter tuned in terms of the width is variable, the learning rates that are chosen are variable, and other aspects of the optimization problem. But in general, their test performances are kind of on par with each other. It's not a place where a neural network in this setting really shines, I think, or outperforms GP. So it was intriguing for us, at least at the level of performance. At that time, we didn't really know what the relationship between the Bayesian, doing Bayesian inference with the Gaussian process in this limit and the finite width network was, but as you'll see, we're kind of building towards understanding that better and better. And this is for the case, again, of fully connected networks. So maybe some remarks before I move on. What we have here is that the manner in which we commonly initialize neural networks yields an especially simple description of the network in function space, namely Gaussian processes. It kind of opens up the question, as Radford Neal actually posed in his original paper for the single hidden layer case, should we be initializing so that in our infinite width limit, we're actually targeting a different class of functions? And maybe that's interesting just separate from any theory of deep learning in terms of scientific applications or places where we other settings other than like image classification where we want to use deep neural networks, maybe some of those choices are actually quite good and we should reconsider them again. The second point, which I already mentioned, is that like from the perspective of performance, you don't seem to benefit a lot from SGD here. And this really turns out to be, at least empirically what we observed was that this was particular to this fully connected network setting and not true necessarily for other architectures. But in any case, given this realization that you can kind of take an infinite width limit, apply the central limit theorem, map something out onto a Gaussian field theory, write down recursion relationships, you can imagine playing the same game with other richer architectures that we know of, where you take some relevant dimension to be infinite. And naturally, the next case to consider is the convolutional neural network. I won't discuss this one in depth, but just kind of highlight some of the main takeaways. The paper itself has a lot more detail in it. But here, so just as a reminder, the number of channels is the thing that plays the role of the number of hidden nodes. And what you have to do is just keep track of an extra spatial index. The notation that I've written up here is particular to the case of one dimension. So z to the L is after L layers. I here indexes which channel we're talking about, and we're going to take I running from 1 to infinity. And then alpha is just a 1D spatial index. Of course, it's like 2D or 3D depending on your problem, but here, just for notation, alpha is a 1D index. This is the sort of computation you do when you apply convolution with a filter that has a size of 2k plus 1. And the only difference now here is after you take the infinite width limit to compute the covariance function, you have these extra indices, alpha, alpha prime, hanging around in addition to the original dependence on the arguments x and x prime. You can see here actually what ends up happening is that to compute the covariance for spatial locations alpha, alpha prime, what you need, the information you need is kind of in the vicinity of alpha, alpha prime from the previous layer. You're going to sum over beta, where beta ranges over some small filter size, the information from the previous layer. That's kind of what's induced by doing convolutions and having weight tying in here. And this is all described in this paper from ICLR of this past year. So I won't talk about more details of the covariance function. I'll just say that, of course, with CNNs, you have many more architectural design choices, and even more than we were able to consider. I think for future work, it would be very interesting for other people to also consider that like large class and kind of explore what happens when you have pooling in intermediate layers or different strides and things like that. We considered two main classes, which were basically with global average pooling at the very end of the network versus without, and you can read more about those details also in the paper. But the table I did want to flash up here was basically kind of the analog experiment that I described earlier for the fully connected case, which was that we took this, we did Bayesian inference with this Gaussian process, now with these convolutional kernels, and then compared to the performance of finite width SGD trained neural networks that were also convolutional and of the same class. So imagine just like L layers of convolutions and maybe terminated with global average pooling at the very end. And here indeed, we did see performance differences. We don't have, this table doesn't have the data for all the cases, but maybe one class that I want to highlight is in the second block, which was actually, it's not the case with pooling, it's just networks with pure convolutions and then just a vectorization at the very end. But even in this case, you kind of see that there are interesting performance differences. So a CNN Gaussian process, which is this linear algebra computation I mentioned, gets this about 32% test error. If you restrict a finite width CNN to a small learning rate, you kind of get a similar test error. If you take a CNN with an ERF nonlinearity rather than ReLU, and you do full hyperparameter sweep over learning rate, you get, again, a similar test error. But when you have CNNs with ReLU and larger learning rates, so you've really hyperparameter tuned this one, you do noticeably better. And this is not supposed to be an all-exhaustive kind of investigation of these comparisons, but it's intriguing that basically when the thing is very hyperparameter optimized, the performance is better. But there are regimes, and even with a certain choice of nonlinearity, but any learning rate for which you do kind of the same as the CNN GP, or as this Gaussian process that comes from the infinite width limit. And these distinctions, again, didn't really show up in the fully connected case where these numbers are kind of reproduced down here. So this top line kind of repeats what I just said. I'll refer you to the paper for many more empirical results. And now before I switch gears to kind of talking about moving away from Bayesian inference and talking about gradient descent, I do want to maybe make a side advertisement for a very nice code base that's been developed, not by myself, but my collaborators at Google, which is essentially would allow you to kind of compute the kernel for a very rich class of architectures. So you can check this out here at this GitHub link. There's also a paper, but it was sort of the initial code base for a lot of the experiments that I've shown you, and so there, you can do a lot more exploration of like constructing kernels, doing Gaussian process inference, and a bunch of other tools as well. I don't have too much more. So in the very last part, I'll just talk about now kind of the evolution of this line of research. So this was, when we started this, it wasn't clear that we weren't necessarily setting out to solve the overparameterization mystery. It was just like an initial motivation in the back of our heads. Along the way, what we've acquired are like a correspondence with Gaussian processes. We can do Bayesian inference with infinite width networks. But now we're going to return to sort of that main question, which is how do we describe learning dynamics in the very large width regime? And down the road, can we say things about like generalization and things like that? So before I kind of get into what we did, I want to highlight maybe a nice, I think, very significant theoretical result from NeurIPS of last year, which some of you may know, which is this neural tangent kernel result. Before I talk about that, I want to maybe just highlight this sort of decomposition, which is that you can do to think about the evolution of a function, completely generic actually, which is trivial but kind of illuminating, I think, to think about. And that's to maybe, rather than like look at the gradient descent equations on the parameters, let's look at the evolution of the function and decompose that into two pieces that maybe would have a little bit different, would have different properties. Maybe we would make different approximations for them down the road. And so the idea is, imagine that this is written in continuous time. You can do the discrete case as well. But here's the differential equation that governs the parameters, theta sub I, so an individual parameter in the network. It's minus the learning rate times the gradient on that parameter. I can decompose that into, just from chain rule, the derivative with respect to the output values of the network times the derivative of the output values with respect to the parameters. So just these zx, this z here is the final network z. It's the actual, let's say, scalar output. It's being evaluated on the training data, x sub a. But I'm just doing chain rule here to kind of tease out the part that has to do with the map that's learned versus the error term, which is kind of the residuals here, which is this first thing. And so imagine now that I wanted to track the evolution of the function, z of x, here again just a scalar. Again, I would do chain rule, I would plug this in, and I would see that that the evolution of the function is basically governed by this quantity here, which is a contraction over the derivatives of the input-output map with respect to the parameters, summed over all the parameters I. And that's a quantity here that we're gonna call it theta. It depends on the two arguments, xa here, which is a training point, and an arbitrary input x, which is where the function is being evaluated. And in general, it's a function of time. So it's a dynamical variable. And it governs the evolution of the function by multiplying in with these gradients of the loss with respect to the input-output map. So this equation by itself doesn't do much because like the core difficulty is that it's not closed in general. So this has some dependence on z, and I don't know what to do with that. I mean, it's a dynamical variable itself, which I need to solve for. It has its own equation and so on. And you haven't really simplified the problem yet. But what the neural tangent, this paper kind of observed is that in the infinite width limit, if you thought of this as a dynamical variable, this is a frozen dynamical variable. It doesn't evolve. And that has to do with the way we initialize neural networks, coming back to the point I made earlier about how the variance of an individual weight scales as 1 over n. So if you were to maybe make back of the envelope estimates, I think these are for a single hidden layer written up here, of what the gradient per parameter, or what the evolution per parameter, or the evolution of an intermediate layer preactivation function, an individual one, how they would scale with width. In the infinite width limit, they would vanish. But nonetheless, what's happening in this problem is that each kind of contribution from a weight or from an individual preactivation is vanishing. Nonetheless, they have some collective effect which allows you to learn some O1 change in the actual function value at the very end. I'm going to jump ahead a little bit. I'll just say that now that this kernel is frozen, and I refer to that here as theta, it's really coming from these gradients. One part of that is actually very much related to the neural network, this kernel I talked about earlier from the Gaussian process correspondence, which is K, plus some of these other pieces which also involve Ks from previous layers. So there's an intimate relationship between the recursion relationship for this new kernel, the neural tangent kernel theta, and the old kernel that I was talking about. So this was all in function space. one of the papers that we had published in this conference was about what happens in parameter space. So how do the parameters evolve, and what kind of model effectively realizes these dynamics? It turns out that the dynamics is equivalent to just linearizing the neural network about the initial parameters. So if you have this function z of x, you do a first-order Taylor expansion with respect to the parameters, and if you looked at the dynamics of that problem, they would be equivalent to NTK dynamics. And so in addition to the evolution of the function that you can get in closed form for MSC loss, you can get expressions for the evolution of the parameters as well in this limit. You can get other nice expressions for the predictive posterior distribution under this gradient flow. I haven't written out those expressions, but I refer you to the paper for those. And also empirically, you can check that as you make, if you take a neural network of any depth and make it wider and wider, eventually you reach this NTK regime. And if you tracked the change in parameters overall, how they scaled with width, if you track the change in this NTK kernel or any other kernel, how that scaled with width, you would find that they vanish in the infinite width limit. That's all of these trends that show these differences kind of going down. We've also, in general, one thing we qualitatively sort of find is that how rapidly you kind of approach this infinite width limit depends on the data set size that you're training on. So it becomes worse the larger you make the data set size. So that kind of has a reverse effect. Really, to be in this NTK regime, you kind of want width to be your largest parameter in the problem compared to depth, compared to data set size. But pinning down exactly when we are in this regime or not is something that I'll come back to. I think requires a lot more investigation as well. Here are just two, I'll skip to this one, some empirical comparisons showing a nonlinear network evolution in function space, and also the losses in accuracy in comparison to this linearized approximation. So you just do the first order Taylor expansion, train it, and see how it does. And this is a model that already starts to have some of the core elements that we have in more realistic neural networks. It's a wide ResNet type model with just one block. It's very wide. And you see that you can actually get a kind of decent description. That's the difference between the dashed and the not dashed lines, the solid lines. You can get a pretty decent agreement between the nonlinear and linearized model out to some late times. I'll skip over this. And maybe just say a couple words of conclusion. So one thing, given this workshop is about also applications to science, just completely separate from kind of what I really wanted to talk about, I think what we've done inadvertently in this limit is also uncovered a very rich class of Gaussian processes and kernels that perform really well, better than anything that had existed up to this time. And so for science applications, I think that they're really worth investigating. You can check out the code base, the neural tangents library, if you'd like to use it for science problems. So there's a lot. I think it opens up new research directions in sort of kernel design. What's really behind these good performing kernels? Compositional kernels, they're non-local, etc. To maybe return to my original thread, and this is my last slide, I promise, to go back to developing a theory of deep neural networks and where are we now. So we've figured out what's happening in the infinite width limit. I think what you want to do, going back to what do you do in theoretical sciences, well, you take a limit, you solve it, and then you do some perturbation theory, and you see if there's a like computationally reasonable way of doing perturbation theory, and if you can use that to describe the network, then kind of that theory, the radius of convergence of that theory kind of encompasses what you want to describe, right? And so that aspect of the problem I think is still kind of open right now. So when people say the infinite width theory is not very useful, I think to really explore that you have to also do the perturbation theory, and you have to also make more precise what question do you exactly want to answer. So are you trying to describe learning dynamics very well? Are you just trying to find measures that correlate with generalization? And I think depending on what you're seeking to do in a theory of deep neural networks within supervised learning, those will have different answers. And once that is done, then I think one can really say, oh, we need a new starting point that's different from the infinite width limit, and probably that one is going to be harder, but I think there remains a lot more to investigate kind of in these questions. So thank you.
We have time for maybe one or two questions, and maybe one of my other organizers can run the microphone because I don't have an ACL right now.
Any questions? Yes.
Hi, I was just wondering how these methods scale with data, if they're using sort of GP kernels start in them.
Yeah, they scale poorly. All of our results were implemented exactly, so they have that like cubic cost in terms of the matrix inversion. I think if the reason we didn't really address that is because we just wanted to kind of do a exact comparison, as exact as possible. But if you're interested in them as a tool or in an application, then I think like one should really connect to the whole body of work on like approximations for GPs and that sort of thing.
Thanks for the very interesting talk. So if I understand correctly, SGD on a neural network with width infinity is equivalent to GP as long as the loss is minuscule error, right? Mm-hmm. Is that right?
Yeah.
Okay.
Yes.
Thank you.
And to see that, you can both look at our paper published in this conference and the neural tangent kernel paper and others that are cited.
Okay, yeah. Last question.
Thanks for a great talk. So, I mean, speaking about your generalization error, I mean, are you sort of considering that could you understand in terms of the kernel that suddenly you don't have control over the length scale of the kernel any longer when a model suddenly do not generalize well, that you due to a wrong initialization or something actually get into kernels that are completely wild? Or what's your view on that?
Yeah, I think that's a connection that should be further explored. There is like one paper I know of that's out there already kind of looking at the kind of fixed points of the recursion relationship and relationship to generalization. But in general, the thing that I was showing earlier for signal propagation was just about the poor conditioning of the kernel, like just training. So just the like on the training data. But also there's a question of like what kind of conditioning would you need for good generalization?